So, how do we find values of p for which the knot is p-colorable? So in the last one, I just told you, hey, the trefoil is 3-colorable, and this is why it's 3-colorable. I had information that you did not know going into that example, right? So, so let's say I give you a diagram of the figure 8 knot over here. Actually, I want to. No, let's keep that stuff. Might as well. Okay, so here's a diagram of the figure 8 knot, and the idea is, well, let's assign variables to each strand. So this first strand right here will be labeled by the variable x1. This second strand right here gets the label x2. This one gets x3, and this one gets x4. Yeah, there are 4 crossings here, and therefore there are 4 equations, linear equations, that need to be satisfied for this to be p-colorable. And what are those equations? So the first equation, so right here I need 2 times the overstrand, which is x2, is equal to the sum of the understrands, which is x1 plus x3. So I need those to be equal. Equivalently, I could just subtract x1 plus x3 on both sides and say that this is congruent to 0 mod p. I could have said that instead. And so that's what I'm going to do for all of these. So for equation 2, I have right here. So I have x3 is my overstrand, and then my understrands are x2 and x4. So I should get 2 times x3 is equal to, what were my understrands? X2 and x4. So I need 2 times x3 is equal to x2 plus x4 mod p, or 2x3 minus x2 minus x4 is congruent to 0. The third one, my overstrand is x1, so I get 2x1 minus my understrands are x3 and x4. Right here, we're over here, x3 right there and x4 right there. And then for the fourth one, my overstrand is x4 and my understrands are x2 and x1. So I get 2x4 minus x1 minus x2. Oh, and these are all congruent to 0 mod p. Okay, so we're going to put these coefficients into a matrix. So it's going to have 4 equations and 4 variables. So let's see, for this first one right here, x1 has the coefficient -1, x2 has the coefficient 2, x3 has the coefficient -1, and then x4 has the coefficient 0. So all these are like kind of ordered pretty weirdly, but we can just like reorder them nicely and put them into this matrix. What is it for the second row? So there's no x1. X2 is -1, x3 is at 2, and then x4 is -1. For row 3, get 2x1 minus x3 minus x4, no x2. 2x4 minus x1 minus x2, that third one. Okay. Let me point something out. So before I talk more about this matrix, let me go back up to our picture of this trefoil that we colored here. If I were to add, say, add 1 to all of these, then how would that affect my equations? So let's see. In this first equation, I would get, so 2 times, instead of 0, I add 1 to 0. And then over here I get 2 plus 1, which is 3, plus 1 plus 1, which is 2. So I get 3 plus 2 is congruent to 2 mod 3. And of course 2 and 5 are 3 apart, so this still holds. And in general, if I were to just do this for a crossing, so let's say that I have x, this one would be y, this is x, this is z. If I have 2x, it's congruent to y plus z mod p. If I already know that this is true, then if I were to add 1 to everything, then what do I get? Well, on the left, I get 2x plus 2. And on the right, I get y plus z plus 2. And then I could just subtract 2 from both sides. And I get the same exact equation that I was working with. So in summary, what I can say here is that if I have one coloring, then I can get another coloring just by adding 1 to all of these things. And I could do this as many times as I want. So really, it could just be adding any number to every single strand. I could add 5 to this, 5 to that, 5 to this, and that would also be a valid 3 coloring. So let's go back down here and talk about why that's relevant. So one reason that that is relevant is that we're going to get infinitely many solutions here. Another thing that's relevant to this matrix, well, actually, before I say that, one thing that you could do to deal with that is just like specify that, you can just specify that x1 has to be 0, or you could do x2 has to be 0, or x3 has to be 0. And this is fine, because if you have a mod p solution, and let's say x1 was equal to 5 in that solution that you found, then you just subtract 5 from every strand, and then your new x1 would be 0, and all of the other strands would just be different. You just subtracted 5 from them. So yeah, we can specify that x1 has to be equal to 0, which would effectively just like make this entire column a column of zeros, because up in my equations, my x1, if my x1 is 0, then all of the x1 terms, like my coefficient, would be 0. So I could just effectively just get rid of that column. The next fact that goes along with this is that if you were to calculate the rank of this matrix, you would find that one of these rows is actually dependent on the other rows. So the set of rows here is linearly dependent. So we can throw out one of these rows, and I'm not going to explain to you why that's true. I don't think it's really worth it for our purposes today, but just kind of take my word for it that that is true. So in summary, it turns out that one row is always a linear combination of the others. So we can delete that row. It doesn't actually matter which row you pick. We could just delete one of them. We can also assume that x1 is equal to 0 by the above discussion to avoid extraneous solutions. And this effectively deletes column 1. So we have our matrix, and then we delete a row and column from it. And then we get a new matrix, which we will calculate the determinant of. So this is our matrix that after we delete a row and column. It doesn't matter which row and column you delete. I just decided to delete the first row and first column. And then we calculate the determinant. And so I'll do cofactor expansion along cofactor expansion along the first column so I can get some zeros. So I'll get -1 times -1, 0, 2, minus 0 times stuff, and then plus -1 times stuff. And then this is equal to this will be -2 minus 0, and then minus, this is -2, minus -1 times -1 is +1. So this is equal to 2 plus 3, which is 5. So the determinant of this matrix was 5. Okay. So one thing that maybe would have been nice to talk about would have been doing linear algebra over different fields. So in particular, doing linear algebra over the field z mod p, which is equal to the set of integers that are between 0 and p minus 1. So if p is a prime, then this is something that you would call a field. I won't talk about what that means exactly, but the idea is that multiplicatively, any number in here that's not equal to 0, there is a different number that you can multiply it by to get that it's equal to 1 mod p. So basically it means that you could divide. And so our equations, we could be viewing them as equations over z mod p. I could just technically be writing is equal to 0 in z mod p for all of these equations up here. And so if all of these equations hold, then, there we go. And so if our determinant, where am I? Yeah, all right. So if our determinant was 5, well, that would mean that our determinant is actually equal to 0 over, so this is equal to 0 mod 5. So in z mod 5, that would mean that this matrix is singular, which means that there are more than one solution. There is more than one solution to this set of equations. So basically, it means that we can solve this matrix mod 5. There's not the unique solution. The unique solution would just be if everything had to be 0. But if this is equal to 0 mod 5, then that would mean that there is a solution. So anyway, the theorem that's really summing up everything that I'm trying to babble on about that maybe is not making a ton of sense right now, is the following. So let M be a matrix for the linear system of equations that look like 2xi minus xj minus xk is congruent to 0. This would be think of it as equal to 0 mod p for each crossing of the knot. So this, you get 1 for each crossing of the knot. Put that into your matrix M. And M prime is obtained by deleting a row in column from M. Then the theorem is that K is p-colorable if and only if the determinant of M prime is a multiple of p, or is congruent to 0 mod p. So yeah, this is just a note that is kind of explaining more what I was talking about. Our equations can be viewed as equations in the field z mod p, which I already talked about. So if the determinant of your matrix is 0 mod p, then that tells you that you have solutions there. So that's why this theorem is true. So the definition that comes from this is the following. The determinant of a knot, K, is, well, maybe I should have written, is written as the determinant of k, and is equal to the absolute value of the determinant of m prime for any m prime, as you would find above. So you start with any diagram of the knot and then find the determinant by that whole process. There are a lot of choices being made in that process, so there's a lot of things to check that would tell you that this thing is actually true, but I'm just telling you it is. And so the determinant of the knot is this well-defined thing up to a change in sign. So maybe you calculated it for the figure 8, and maybe you would get -5, and that's why we have to take a absolute value at the end there. But yeah, so that's the determinant. So the determinant of the figure 8, that is 5, and by the theorem, since 5 is a multiple of 5, then the figure 8 is 5 colorable. The determinant of the trefoil is 3, so the trefoil is 3 colorable, and the determinant of the unknot is 0. The unknot is not colorable for any prime p. So anyway, these are the numbers that I was talking about before that help us distinguish these knots from each other. So because the figure 8 got the number 5, the trefoil gets the number 3, and the unknot gets the number 0, then these knots all must actually be distinct. And yeah, so by the way, keep in mind I did not prove either of these things. I did show you that the trefoil is 3 colorable, but that doesn't mean that the determinant is 3. For example, you could have gotten, you could find one knot that is 3 colorable, but the determinant of that knot is equal to 15, for example. So this knot is colorable mod 3 and mod 5. So just finding a 3 coloring of a knot doesn't tell you that the determinant is 3, but if you find that the determinant is equal to 3, then that would tell you that it's 3 colorable, or if it's any multiple of 3, then it's 3 colorable. Also, there are some knots where the determinant of that knot is equal to 0, but that knot is not equal to the unknot. So this is not like a foolproof way of distinguishing knots from each other. There are more advanced tools that you could develop and figure out and find and calculate for knots that would help you distinguish them better from each other. And so